Hey Pre-Calc students, today in our video we're going to talk about rational functions. We're going to look at possible graph features and features from factored form and features that you can find when you factor your rational equations. So first, a rational function is anything where you are dividing two polynomials. So you have a polynomial, p of x, we call this our numerator, and q of x, which is also a polynomial. So maybe you have a cubic trinomial up top and a quadratic binomial on the bottom. But rational functions come from the division of two polynomial functions. Some features that rational functions can have. So I've kind of grouped these into a few different categories. So things that create errors in our domain, which are holes and vertical asymptotes. Other features that the graphs might have that you might be familiar with from other functions are x-intercepts and y-intercepts. And then in behavior features, slant and horizontal asymptotes. We will cover the in behavior features in a second video. For this video, we're going to focus on the domain errors and our other features, x and y intercepts. So we're just going to focus on these these four features in today's video. So to algebraically identify our features, we're going to start by factoring. In factored form, you're going to have a whole bunch of factors in the numerator and the denominator. Holes are factors that create a zero in both the numerator and the denominator. So holes are something that will have factors numerator and denominator. Vertical asymptotes are factors that create zeros only in the denominator. And these values are not included in the domain. We'll look at the graph of each function so that way we can kind of see what we're talking about. But again, holes, vertical asymptotes, holes are factors in both the numerator and denominator. Vertical asymptotes are creating zeros only in the denominator. So let's take a look at an example. So we're going to identify the holes, the vertical asymptotes, and then we're going to write our domain of the function y equals x minus 4 over 2x squared minus 8x. Our first step is always going to be to factor our rational function, both numerator and denominator. In this rational function, the numerator is prime. It cannot be factored. So I'm going to leave it as x minus 4. My denominator, I see that I have two terms, and both my terms have a 2 in common, and they also have an x in common. So I'm going to GCF factor out a 2x. And then remaining, I would have 2x times x would give me a 2x squared, and 2x times negative 4 would give me a negative 8x. So this is my factored form of my rational function. Once I am in factored form, I can identify two key features. So the first feature I'm going to identify is a hole in the graph. A hole comes from anything that will simplify away. These are our 0 over zeros. If you remember back to limits, whenever you have a factor that creates a 0 in both the top and the bottom, for example, this x minus 4 and this x minus 4 is both in the top and the bottom, so this is going to create a hole. To identify the location of the hole, I'm going to take this factor and I'm going to set it equal to 0. So I have a hole at the value x equals 4. Now, what I can also do is I can also simplify this factored hole, and I can simplify my rational function. This hole does cancel, leaving me with 1 over 2x. And if I wanted to find the y value of the hole, all I need to do is plug this x value into the simplified form. So I have my x value, and to find the y value, I'm going to plug this x value now into my simplified form. So I have a hole at the value 4 and 1/8. Okay, the next thing I want to find is my vertical asymptote. To find my vertical asymptote, I want to take any remaining factors in the denominator. So again, any remaining factor, in this case, I have my 2x that's remaining in the denominator, and I'm going to set it equal to 0 and solve. This tells me my location of my vertical asymptote. So I have a vertical asymptote at x equals 0. Let's take a look at the graph of this function and see these features on the graph. Okay, so looking at our graph of this function, so again, I graphed the original function. You could also graph it in factored form. And the only difference between factored form and the simplified form is the simplified form would look the exact same. It just wouldn't have the domain exclusion hole. So this is the graph of my rational function. I have a vertical asymptote at x equals 0, and I have a hole at 4 1/8. Just to kind of show you guys really quickly, if I was going to write the domain of this function, the domain starts at -infinity, goes up to that vertical asymptote, but won't include the vertical asymptote, go from the vertical asymptote to the whole value, so at x equals 4. We're not going to include the 4, and we'll then go from 4 to infinity. So we've got the whole at 4 1/8. If you're graphing in Desmos, Desmos won't actually show the hole on the graph, so I have it plotted on a second line. But if you trace the graph with your cursor and you go over 4, you'll see that the value 4 is undefined on the graph. So there is a hole here at 4 1/8, and then we also have the vertical asymptote at x equals 0. Okay, the next two problems we're going to try mostly on our own. First thing I want you to do is step 1 is to factor. So can you pause the video and factor both of these rational functions? We'll start with number 1 and then number 2. Okay, check your factoring work. And then we're going to do holes for both of the graphs. So can you find the hole in the first and the hole in the second? Pause the video and see if you can do this on your own. Okay, our first graph of this rational function is actually not going to have a hole at all. The hole, I don't have a factor that matches in the top and the bottom, so I can say that there is no hole in this graph. And some functions will have some features, but not all features. So this is a graph that won't actually have a hole. In my second function, I do have a matching factor of x minus 3. At x minus 3, if I set that equal to 0, I get 3, I get the 3. And then I can use that value to plug into the simplified form to find the y value. So plugging 3 into x minus 3 over 4, and that gives me 0. So my hole is located at 3, 0. Next, we're going to talk vertical asymptotes. So we're going to find our vertical asymptotes for each graph. And pause the video and see if you can try this on your own. Okay, so for my vertical asymptotes, you're using what is remaining in the denominator once you eliminate your holes. Well, here in my first, I have x plus 1, set it equal to 0. I have a vertical asymptote at -1. In my second one, I have only 4 left in the denominator, and if I try to set 4 equal to 0, that can never happen, so there is no vertical asymptote in the graph. I'm going to pull the graphs for both of these functions, and then we'll talk about the domain. Okay, when inspecting our graphs, the first function doesn't have a hole in it, but it does have a vertical asymptote here at x equals -1. So that's where that graph is splitting. As x approaches -1 from the left side, it's going to infinity. As x approaches -1 from the right side, it's going down to -infinity. So again, vertical asymptote here at -1. On my other graph, I don't have a vertical asymptote, but I do have a hole here at 0, 3. And essentially, when I simplify this graph, all I have is x minus 3 over 4. This is a linear function. It just has a hole in it. So this rational, when I graph it, actually looks like a straight line. It just has a hole in the place of 3, 0. See if you can pause the video and write the domain of these two functions on your own. Check your domain work, and then we'll keep working. Okay, the last thing that we're going to talk about in this video is how to identify intercepts algebraically. To find a y-intercept, The function will always cross the y-axis when x is 0, so you're just going to plug in 0. So you're going to let x equal 0 and find y, and that's how you find a y-intercept for any function. To find an x-intercept, you're going to set the non-whole factors left in the numerator equal to 0. So we've been talking about factors in the top and the bottom. Those create wholes. Factors just in the bottom that create zeros are vertical asymptotes. Factors just in the numerator are going to create x-intercepts. So let's take a look at those, going back to those three functions that we just did, and we'll find the y-intercept and the x-intercept of each. Okay, here are our three functions. Really quickly, I'm going to get their factored form below them. Okay, so the first thing I'm going to do is talk about how do we find the y-intercept. So to find the y-intercept, you're going to let x be 0. X is always 0, and we're just going to plug that in and find y. So for my first equation, I've got y equals 0 minus 4 over 2 times 0 times 0 minus 4. And I'm going to simplify this. So my numerator simplifies to negative 4. My denominator, I have 2 times 0, which is 0. And then I have 0 minus 4, which is negative 4. So this will simplify to negative 4 over 0. Negative 4 over 0 is a not number, right? I can't divide negative 4 by 0. So this is an error, or we would say undefined. So my first equation does not have a y-intercept. The y-intercept is undefined. We'll get the graphs back here in just a minute and look at those, but see if you can find your y-intercepts of the other two equations. Okay, check your y-intercept work. When you plug in 0 into the second one, you get negative 9. So I have a y-intercept of 0, negative 9. For my third one, when I plug in 0, I can reduce this fraction to negative 3/4. So my y-intercept is at 0, negative 3/4. Okay, now let's talk about finding my x-intercepts, and I need a little bit more room. X-intercepts come from factors that are not wholes in the numerator. So if I look at my very first equation, I had this matching factor in the numerator, and that created the whole. After that, I didn't really have any factors remaining, so this graph doesn't have any x-intercepts. It has none. Because this one doesn't have any, I'll also talk through the second one. I'll find the first x-intercept of the second one. So my second graph didn't have any matching factors top and bottom, didn't have any wholes. So my two remaining factors are going to create my x-intercepts. So when I create my x-intercepts, I'm going to set these factors equal to 0 and solve. Okay, I did the first one, x minus 3 equals 0, set it equal to 0, and found the x-intercept of 3. See if you can do the other one on your own. So I got two x-intercepts at 3 and negative 3. You can probably leave them like this, but if you want to write them as points, x-intercepts are on the x-axis, so they'll be at the point 3, 0 and at negative 3, 0. Okay, try the last one on your own. Okay, so this one has an x-intercept at x equals 3. So 3, 0. But something really interesting happens in this graph, and when I pull up the graphs, we'll talk about that in just a moment. So I'm going to get the graphs of all three of our functions. Okay, for space and organization, I'm going to talk about these graphs one at a time. So my first equation, it had no y-intercept. The y-intercept was undefined, and I didn't have an x-intercept. And if I look at the graph, I have a vertical asymptote at x equals 0, and I can also see on my graph a horizontal asymptote at y equals 0. So this graph will never cross the y-axis, nor will it ever cross the x-axis. So that's why both of these are no y-intercept and no x-intercept. Okay, looking at my second graph, I had a y-intercept at negative 9, at 0, negative 9. So at 0, the graph is crossing the y-axis at negative 9. And again, all we did was plug in 0 to find that point. And then to find my x-intercepts, we plugged into our remaining factors, and I have two x-intercepts at -3 and at +3. So that's that graph. Okay, so this graph, we have a y-intercept at 0, -3/4. So 0, -3/4 crosses the y-axis. But then I have something really interesting that happens here. I had found that I had an x-intercept at 3, 0. But if you remember, 3, 0 was a hole. Because the hole is there, there's an undefined value, and so even though it looks like it's going to cross the x-axis, it actually is undefined. So even though we found the hole at 3, 0, we're going to say that there is no x-intercept because that value is technically a hole and not an x-intercept. That's it for x-intercepts, y-intercepts, holes, and vertical asymptotes. We'll talk more about this stuff tomorrow in class.